The number of star rotations is always one greater than our sun's rotations. Mean solar days are always longer than sidereal days by 3 minutes 56 seconds. Special coefficients allow astronomers to accurately convert solar time into stable sidereal time. Every day, sidereal time gains about 4 minutes relative to our mean solar time.
All right, let's talk about time. We live our lives by the 24-hour clock, right? But what if I told you that a day, well, it isn't really 24 hours long? The real answer is a bit more complex, and it all boils down to whether you're measuring your day against the sun or against the incredibly distant stars. So that brings us to a really fundamental question. What truly is a single full rotation of our planet? Now, if you asked most people, they'd say 24 hours, and for our day-to-day lives, that answer works perfectly fine. But from an astronomical perspective, that's not the whole story. The real answer depends entirely on your frame of reference.
Okay, so here's our roadmap for this discussion. We're going to start with the two celestial time standards. Then we'll dig into the core reason for the discrepancy between them. We'll quantify that difference, look at the mathematical formulas for converting between the two, and finally, we'll see how this is all applied in practical, observational astronomy.
All right, let's dive right in. The first thing we need to understand is that there are two fundamental ways to measure a day, and it all depends on which celestial object you use as your stopwatch.
First up, you've got the mean solar day. This is the one we all know and live by. It's based on the sun's position in the sky, and it's the foundation for our clocks and calendars. Then there's the sidereal day. This is the astronomer's time. It uses the seemingly motionless backdrop of distant stars as its reference point. And this simple change in perspective is where all the interesting physics begins.
So the big question is, why? Why are these 2 days different lengths at all? Well, the secret isn't just one motion, but two distinct movements of the Earth that are happening at the exact same time. First, you've got rotation. Picture the Earth spinning like a top on its axis. That's what gives us day and night. But at the same time, there's revolution. Imagine the Earth gliding along a massive track around the sun. That's what gives us a year. The absolute key here is to remember that as our planet is spinning, it's also constantly moving forward in its orbit. That compound motion changes everything. Okay, let's really visualize this. Imagine you're standing on Earth, and you draw a laser straight line out to a very, very distant star, light years away. A sidereal day is the time it takes for Earth to spin exactly 360 degrees, a perfect circle, so that your imaginary line points right back at that exact same star. It is a true, complete rotation. And how long does that perfect 360-degree spin take? 23 hours, 56 minutes, and about 4 seconds. Now hold on a second. That is not 24 hours. So from a pure, unadulterated physics perspective, this number is the true rotational period of the Earth. Okay, so that's the star perspective. Now let's bring our own star, the sun, back into the equation. During those 23 hours and 56 minutes, as the Earth was completing its perfect spin, it was also traveling a little ways along its orbit. So to get the sun back to the exact same position in the sky, say high noon, the Earth actually has to rotate a little bit extra. Think of it this way. After spinning a full 360 degrees, we've moved. So to get the sun back to that same overhead meridian, we have to turn just a little bit more to catch up to where the sun now appears to be. That extra little turn is about 1 degree. And what does that extra 1 degree of rotation cost us in time? Well, it takes about 3 minutes and 56 seconds. And what happens when you add that extra time to the true sidereal day? You guessed it. You land right at our familiar 24-hour solar day. That's our so-called missing 4 minutes. So, okay, a 4-minute difference each day. It doesn't sound like a lot, right? But you let that accumulate over an entire year, and it adds up to something truly significant. Let's look at the cumulative effect. This is where it gets a little mind-bending. That full journey around the sun, that one revolution, actually counts as one extra full rotation of the Earth relative to the distant stars. It's almost like a freebie rotation we get just for completing an orbit. And what that means mathematically is that a year must have exactly one more sidereal day than it has solar days. We all know this number, right? Roughly 365¼ solar days in a tropical year. This is our baseline, counting how many times the sun has returned to the same meridian in our sky. But If you count the number of times the Earth has completed a true 360-degree spin relative to the stars, you get 366 and a quarter sidereal days. And there it is. That's the extra day. It's the cumulative effect of that tiny 4-minute difference, day in and day out. You could almost call it a ghost day, one created entirely by our planet's orbit.
All right, so we've nailed the concept. Now let's get into the mathematics of it. Astronomers, of course, can't just eyeball this. They need precise formulas to convert between these two time systems.
So the first key is a conversion factor that we'll call K. You get it by dividing the number of sidereal days in a year by the number of solar days. And since there are more sidereal days, this number is just a tiny bit larger than 1. Think of it this way. It's a number that tells you exactly how much faster the sidereal clock is running compared to our everyday clock.
And as you'd expect to go the other direction, we use another factor, K prime. It's simply the inverse, solar days divided by sidereal days. So this number is just a little under 1. It's what you use to translate a sidereal time interval back into the mean solar time we're all familiar with.
And this table here really lays it all out beautifully. You can see a 24-hour solar day is equivalent to 24 hours, 3 minutes, and about 56 seconds of sidereal time. And look at the flip side. A 24-hour sidereal day is our familiar 23 hours, 56 minutes, and 4 seconds. You know, for a quick rule of thumb, just remember that one sidereal hour is about 10 seconds shorter than a solar hour.
Okay, theory and formulas are great, but how is this actually used? Why is this so critical for, say, observational astronomy? Well, if you're trying to point a massive telescope at a tiny, distant object, your wristwatch is basically useless. You need to know the sidereal time, and you need to know it with extreme precision.
So one way to think about it is working backward. If you have an instrument that tells you the current sidereal time, S, and you know the sidereal time at the last midnight, S, you can just find the difference. That gives you the sidereal time that's passed since midnight. Then you just multiply by that K prime factor to convert it back into the mean solar time you see on your clock.
But in reality, it usually works the other way around. An astronomer knows their local time and needs to find the sidereal time. Now, the process might look a little intimidating, but the logic is pretty straightforward. You start with a known reference point, the sidereal time at Greenwich at midnight, from an almanac. You adjust that for your specific longitude. Then you calculate how much solar time has passed since your local midnight, convert that into a sidereal interval using our factor K, and add it all up. And that's it. You've got the current local sidereal time, the key that unlocks the coordinate system of the sky.
And you know, there's actually a pretty neat shortcut for approximating this. Look at this table. Around the September equinox, at midnight, the solar and sidereal clocks are basically in sync. But then, as the Earth moves in its orbit, the sidereal clock at midnight gets ahead. By December, it's 6 hours ahead. By March, 12 hours. By June, 18 hours. It completes a full 24-hour cycle throughout the year. It's a beautiful, predictable rhythm. And all of this brings us to one last, really profound question. We've established that the sidereal day is the true, pure measure of Earth's rotation from a physics standpoint. So why have we, as a civilization, built our entire world, our schedules, our economies, our very concept of a day around the solar day, which is, astronomically speaking, less precise? The answer, I think, has less to do with cosmic accuracy and everything to do with our fundamental relationship to the star that gives us light, warmth, and life.
Thank you, friends. Strive for understanding and become wiser. See you soon.